Good. Then let's continue from here. So before the break, what we showed is that when you start from a lattice model, then you can derive by a set of a bit heuristic arguments a free energy functional, the Ginzburg-Landau functional, or in this case the Frey-Huggins free energy functional. It has this characteristic form of a local free energy density and a gradient square term. The local free energy density has a mixing entropy term and an interaction term. The interaction term contains the Frey-Huggins parameter, and so is the interaction term here that penalizes gradients in phi. And I've written it here out in detail. So there's constants, but basically the C is the same as chi in units of kBt. That's the important information. Now, since we say we somehow want to simplify things and work with a polynomial free energy instead of the logarithms, maybe just for mathematical convenience, then you can say, let's just take the free energy that we have and note that we can expand it around the threshold value, phi c equal a half, so right in the middle. And then we get this classical form of a free energy functional that has the same structure as the one we know from the Ising model. Okay? And that's also quite nice because we have explicitly shown it doesn't really matter whether we talk about magnets or binary mixtures, it's the same kind of physics. The difference is that there's prefactors, and these prefactors are characteristic for the problem that we study. 2 minus chi here is the interaction parameter. Chi is this difference of energies between the solvent, the solute, and the mixed interactions. It changes sign at chi equal 2. This flips concave to convex, convex to concave, and this here is stabilizing, and that term is again penalizing gradients in phi. Now for the following, it's even more convenient to go back to concentration. So phi is a volume fraction, and if I define volume fraction divided by molecular volume, I get an actual particle density, so number of particles per volume. And then if you do that, you can rewrite the free energy in this form. The free energy F is equal to an integral over space, let's say three-dimensional space, and then I have minus a half R C minus CC squared. Just for your convenience, this R is basically a chi minus 2, but there's constants 2 kBt chi minus 2 times V. Now we have it in the same form as for the Ising model. Then we do have here plus a quarter U C minus CC to the fourth. The parameter U is 16 over 3 kBt times molecular volume to the third power. And then we have higher order terms, plus a half times kappa times nabla of C squared, where our kappa is this kappa tilde, which is this expression here, times kBt over the molecular volume. And you shouldn't really worry about these detailed relations between the coefficients. In the end, these are phenomenological parameters, and all that matters is that this is a constant, and this is a constant, and those constants have a positive sign, and this r here that you have flips the sign as you go through the critical point, which is chi equals to 2 in our case. All right, and now if you like, maybe you can do this for yourself as an exercise. You can use that kind of free energy landscape that we have there, or one where you break the symmetry by adding a term. Add here something that has a cubic term, then you tilt the symmetry, you make the free energy landscape asymmetric, and then you can go through just the same kind of math. What's the Maxwell construction? What's the binodal? What's the spinodal? What are the corresponding expressions? That's not hard. It's just a matter of doing the math. Now, what I wanted to discuss with you is interface tension. We had this before, but I think it's good to talk about interface and surface tension here once more. Just to set the notation straight. So in the limit of space going to plus or minus infinity, I want my interface profile to be such that it approaches the minima of the free energy. So I want it to approach either this and that minimum or the equal minima that you see here. And I write it down for the case that it's symmetric. Then this is the critical value. So phi c over volume plus or minus the square root of r over u. And this is a profile that goes from a value c minus to a value of c plus as a function of x, which is the coordinate perpendicular to the interface. And you can shift, of course, the position of the interface here. And in the end, I want it such that this has an inflection point right at the origin. Okay, so this profile, as you know, is given by the fact that this should relax to thermodynamic equilibrium. So the functional derivative of the free energy functional with respect to c should be 0, defining a stationary solution of our free energy density. Well, we can do that, right? Here is the free energy density. You can take the functional derivative of that. For the local part, this is just the derivative. And here, from the Euler-Lagrange formula, we get the Laplacian. So that means, in that case, you get f prime as a function of c twiddle minus kappa dx squared c equal to 0. And let me add here this tilde, and this then denotes the stationary profile. You can also write this more explicitly. So if I use my free energy that we just had, then taking the derivative of the local part is minus r prime delta c of x plus u delta c of x to the third power minus kappa times the Laplacian of delta c of x equal to 0. And my delta C, just as before, is given by the profile in reference to this critical value CC. That's a differential equation that you can solve. I've shown you how to solve this last time for the Ising model. Here you can go along similar lines, and of course the solution you get from that is a hyperbolic tangent centered around the threshold value. The amplitude is given by the asymptotic values of the minima, so plus or minus r over u, and this is connected by a hyperbolic tangent with a width psi, and this width psi is 2 times kappa divided by r. You've seen this before, right? This is a width that scales with the interaction parameter, and it becomes infinite when you approach the critical point where r is equal to 0. All right, now interface tension we can define as usual by the cost that we have for making such an interface as compared to the case where you don't have such an interface. So our gamma is defined as an integral over the whole domain from minus to plus infinity. The free energy evaluated for the profile, the gradient term also evaluated for the profile, and I have to subtract things where I don't have curvature, so I'm just integrating then over the domain to the left with the value of f at C minus, and I'm also subtracting a flat profile on the right, which is evaluated the free energy at C plus. That's our definition of the interface tension, and now I have to evaluate that. And you might remember that for the case we studied before in the Ising system, that this term and that term were basically the same. Here this is true as well. You can combine this term and the terms which you subtract to be identical to the first term. So what you get from that is that your gamma is given by an integral from minus to plus infinity dx kappa gradient x of the profile squared. And that you can again, also as before, write as an integral over the profile, changing variables, kappa dx c twiddle. So this looks now as an integral over the gradient of the profile. And again, by the same relation that I used here, namely that that term is the same as the remainder in the equation, you can write this as an integral from C minus to C plus over C tilde, and I'm integrating the free energy evaluated at C tilde minus the free energy at one of the minima, and here I choose it to be C plus. So as before, the surface tension is just a property of the free energy density evaluated as a function of the concentration. questions? Yeah.
Could you remind how do we get rid of those? How do we cancel those terms?
This is the same calculation as before, and all you use is that they are solutions of this differential equation. And then you see this quite immediately. It's not difficult, right? It's really just using the differential equation the same way as before. You can check it on the notes. It's there in detail. It's important, though, so it's not a minor thing, because the final equation that we have here says that I don't have to know the profile to know the surface tension. It's a property of the free energy landscape alone, without even calculating the profile. Okay, let me show you the profile once more so you see how it looks like. Okay, so this is the profile that you have for our case where we expand around the critical point right here. This is kind of a summary slide with the characteristic concentrations. You have the spinodal, you have the binodal defining the gap of miscibility in this region where you have then formation of a domain boundary. The domain boundary looks like so, interpolating between C minus and C plus here and there. The width of that profile is given by psi. Psi goes like the Flory-Huggins parameter, basically divided by 2 minus chi, and the interface tension is given by the free energy landscape. Okay, now that we have that, I want to go to dynamics again and show you how you calculate the stability of the system. So, dynamics. This is the Cahn-Hilliard equation. You have seen the basics already, and I argue very much in the same way. We have the concentration being a conserved quantity. Therefore, it must obey a continuity equation with a current. The current, according to principles of nonequilibrium thermodynamics, so Onsager's theory, has to be to leading order such that it relaxes to equilibrium. So it's a kinetic coefficient, the Onsager coefficient times the gradient of the chemical potential. What's different now, though, is that before when we calculated that, we had just had the free energy density and not a term that contains the gradient of phi. Right? When you look here, our free energy is now functional, containing the local term and this gradient term. So the chemical potential that we have is now the functional derivative of our free energy density as a function of concentration with respect to concentration. And that is, as before, the first derivative of the free energy as a function of local concentration. That didn't change, but now because you take the functional derivative of these gradient terms, you get a Laplacian term in addition. So minus kappa nabla squared C of x and t. That means when you combine this in total, you have the equation of motion, the temporal change of our concentration field is a kinetic coefficient And what I'm doing here, now let me do this later. So this is nabla squared lambda of C times nabla f prime of C minus kappa nabla squared C. Okay. So this is how you should write it, just inserting all the equations into the expression for the continuity equation. If lambda is a constant, or if it only matters what this is close to our threshold concentration, and the fluctuations are not so important for that term, then you can write it like so. And then you have a gradient squared of f prime of C minus kappa Laplacian of C. Okay. This is our Cahn-Hilliard equation. And this here as well, just in an approximation where you neglect the fluctuations for the kinetic coefficient. All right. Let us now do a linear stability analysis of this equation to learn how the homogeneous steady state becomes unstable. Let's do a linear stability analysis. Short LSA. And what we do there is we say that our spatial profile is given by some homogeneous steady state, C bar, constant in space and time, plus some deviation as a function of R and T. We take that ansatz for the concentration and insert it into the Cahn-Hilliard equation. And then we expand in powers of delta C, keeping only the linear terms. Okay. So we insert and keep linear terms only. Then for that linear term, for the deviation from the homogeneous steady state, we get an equation where now the lambda can be actually really pulled out. It's the onset coefficient at the homogeneous steady state. And deviations that come in here would come to higher order. Then we have the Laplacian. Expanding the free energy around C bar gives not just the first derivative, it gives the second derivative. C bar times delta C of R and T minus kappa nabla squared delta C of R and T. That's all that remains. Our other terms are higher order. So plus order delta C squared. Now we have a linear equation. This linear equation we can solve by Fourier transform. So let's do that. We say that delta C of R and T is decomposed into Fourier modes. So this is an integral over in general, a d-dimensional space. Then I have delta c of wave vector and t, e to the I q times r. And when you do that Fourier decomposition, you get a normal mode equation that says delta t, delta c of q and t is sigma of q times delta c of q and t, with the sigma of q simply given by f double prime. Of course, you have to also take the nabla squared, right? So this gives you minus lambda c bar q squared from the prefactor and the nabla squared times f double prime at c bar plus kappa q to the power 2. And it depends only on the absolute value of q. It doesn't on the magnitude of q and not on the direction of q. All right, so this is a dispersion relation because it tells us about the growth rate of the various modes that we have. And this is best illustrated if you actually plot it as a function of wave vector q for the various cases. So here we plot sigma of q. Now the first thing you should realize when looking at this dispersion relation is it has a prefactor which is q squared. And this prefactor q squared has its origin in the fact that you have a conservation law. So when you trace it back, the q squared ultimately comes from the gradient of J, and J being the gradient of a chemical potential. And that you didn't have in the model A that we discussed previously for the Ising model, where you didn't have a conservation law. So this was not starting like q squared. So it means whatever you do, you have to have 0 here at q equal to 0, indicating the conservation law. And then two cases can happen. One is that you do have this bending down. So well, when is that the case? That's the case if this is here negative. And that means, because that's always positive, that I have to have f double prime being positive. So you have a convex structure. And that just recapitulates what we had in the thermodynamics. If a thermodynamic free energy landscape is convex, then the corresponding state is stable to small perturbations. And that's what you recover here for the linear stability analysis in the dynamics as well. Okay. On the other hand, if we do have a f double prime that's concave, so is negative, then when you go to q equal to 0, this is the dominating term, which is negative times the negative prefactor. So it will start out quadratically, like so, initially. Okay, the system becomes unstable because your free energy landscape has the wrong sign. It's concave instead of convex. There's something that stabilizes modes at higher values of q, which is our kappa. This is what is penalizing any kind of spatial gradients. So ultimately, this kappa q squared will pull the dispersion relation down, and you'll get just a band of unstable modes. And this band of unstable modes has two characteristic wave numbers. One is the edge, Q0 of the band, where it becomes, sigma becomes 0, and the other one is Q max, indicating the maximum growth rate. And they are given as follows. So Q max is given by the square root of minus f double prime at the homogeneous steady state divided by 2 times kappa. And Q0, the band, is given by the very same looking expression, just divided by kappa instead of 2 kappa. The fastest growing mode that you see is the one that grows the fastest as you start from a homogeneous steady state. So as you start from some random perturbation of the initial state, the system will pick out this wavelength. And then something else happens, which is beyond our linear stability analysis. And I'm going to show you now how this looks like. All right, so what we have is our phase diagram, where I'm plotting now the concentration. Here's our critical point, and now it's just inverted to before. I'm plotting R and not chi, so it starts from R equal to 0, where the critical point is, and then you have these 2 regions defining spontaneous phase separation within the spinodal and defining nucleation and growth between spinodal and binodal. And now let me show you what happens. So here this is an initial state. And maybe I stop it for you. So the initial state that you see is a random perturbation of a homogeneous steady state. What we picked here is something around 0.5. That's the green color, and some are red and some are blue. So you deviate to larger and smaller values. And then as the system runs, the dynamics runs, you have first a wavelength that's picked. Right? This is a wavelength that's initially picked. And that's the maximally growing wavelength that you see in the dispersion relation. Okay? Then the system is not staying there, but it coarsens. The wavelength that you saw initially is getting larger and larger and larger. Here you have domains shrinking. Here you have them shrinking as well. It's a bit different than before. It's a conserved dynamics, so you can't just have something vanish. It has always to be transported from one place to another, following the conservation law. But otherwise, it's very similar. And as time progresses, the system becomes coarser and coarser and coarser. All right. Questions, yeah?
So, looking at this dispersion relations, would the case, the metastable case, be like start negative and then go positive? Or something?
So okay, good question. So dispersion relation only tells you what happens here in this regime of spontaneous phase separation. It does not inform you at all about what happens between the spinodal and binodal, because there a linear perturbation will give you a relaxation back to the homogeneous steady state. You can read this off from the analysis, actually. Because, right, what I need here to have a dispersion relation that's going up, I need the free energy to be concave. Right? That's what I used. If it's not concave, and here it's not concave, it's actually convex in that regime, you don't have linear instability. So what you need to do in order to create a domain wall between a low density and a high density phase is to have some kind of nucleation site that you put in to push the system over the barrier. You need a perturbation of finite magnitude, and it's a tricky thing to calculate what this finite magnitude perturbation actually is.
So in general, we cannot describe those metastable states within LCA.
No. That's a separate theory. You wouldn't need a theory that calculates the metastable state. There's a way to find the metastable state using numerical continuation of the equation of motion, but you need to look at the full equation of motion and not just at the linearized form. Yeah. Other questions? Yeah.
So we can get a time scale of the maximum frequency from the dispersion reaction, and how should we also worry about the length scale which we use when for the coarse-graining? Because
that's it. Yeah. So I say it again, the linear stability analysis is something that works only in the spinodal, first of all. Second, it only works here. In this first initial phase of the dynamics, where you see that the random perturbation picks a particular wavelength, which is the fastest growing one. From there on, forget about linear stability analysis. It doesn't help you. What you need to do is you need to formulate a theory for the meta-excitation that you see here, namely the interfaces. And then you will have to calculate how the interfaces move and how the motion of the interfaces leads to a change in length scale, and how this ultimately leads to the formation of a single domain of a high density phase in a low density regime. And that's what we do next. That's a separate type of theory, and you can do it. You can actually perform what's called a theory due to Lifshitz, Lossow, and Wagner, where you focus on the interfaces and then calculate how the system coarses. Okay, so for you in general, I mean, linear problems are simple. Very, very simple, because you only have to do a spectral analysis. Nonlinear problems, where the interesting aspect of physics happens here, are very hard, and you usually need to derive a meta-theory for the key excitation, the key defect that you have in the system, and that's, in this case, the interface.